Somewhere in a hospital right now, a machine is annihilating antimatter inside someone's body on purpose to save their life. That's not science fiction. That's a Tuesday. PET scanners, the machines that find tumors by tracking radioactive sugar moving through your bloodstream, work because certain atoms decay by emitting positrons. Antimatter, real antimatter, made inside a hospital, annihilating inside a human chest, thousands of times a day, all over the world. So here's the actual question worth asking, the one almost nobody stops to ask properly. Why does antimatter exist at all? Not, what is it? You already sort of know that. Why does nature bother making it? And why, if it exists, is there so staggeringly little of it left in the entire visible universe? By the end of this video, you'll have one single mechanism that answers both questions at once, something almost no explainer actually does. Because almost everyone tells you only half of this story. You've probably watched a video about antimatter's existence, and a different video about why matter dominates the universe, and never noticed that nobody stitched the two together. That's not an accident. It's genuinely hard to do, because the two halves of this story come from completely different corners of 20th century physics. One from an equation about a single electron, the other from an experiment about a lump of frozen cobalt. This video puts them back together on purpose, because they were never actually two stories to begin with. And there's a third thread we'll pull on too. One almost every antimatter video skips entirely. If antimatter is real, and physicists can already make it in a laboratory, why isn't it powering anything? Why isn't there an antimatter rocket, an antimatter power plant, an antimatter bomb, quietly worrying someone in a government building somewhere? The honest answer to that question turns out to be one of the best ways to understand just how staggeringly rare this leftover matter really is, and we'll get there by the end. You've probably heard antimatter described as some kind of exotic mirror universe stuff, dangerous, alien, science fictional. It isn't. The actual physics is stranger, and once you see it, far more elegant than that. Antimatter isn't a different kind of substance at all. It's ordinary matter described from a completely different angle, one so strange that physicists spent decades arguing about whether to take it literally. Picture a single line drawn across a piece of paper, moving steadily from left to right. Left to right is forward in time. That line represents an electron, just moving through its life the way anything does, existing, one moment after another. Now here's the part that took physics 20 years to accept. Sometimes, in the actual mathematics that correctly predicts how electrons and light interact, that line does something no line should do. It reaches a point, turns around, and starts running right to left, backward. The same single line, now traveling the wrong way across the page. Here's the strange part physicist Richard Feynman pointed out. Formally, in a 1949 paper called The Theory of Positrons, if you, stuck, experiencing time only moving forward the way all of us are, tried to describe that backward-running segment using forward time language, you wouldn't see an electron going backward. You'd see something that looks, in every measurable way, like an ordinary particle except with the opposite electric charge. Same mass, same everything else. Just flipped charge, because you're watching its motion through time from the wrong direction. Feynman didn't invent this out of nowhere. A physicist named Ernst Stuckelberg had the same core insight a few years earlier. Feynman turned it into the working machinery that particle physicists still use every single day. That flipped charge version of the electron is what we call the positron. It's antimatter. And under this description, it isn't a separate kind of thing. It's the exact same electron, just running the other way through time. That single idea, one line, two directions, turns out to explain something that had already been discovered, but not really understood. In 1928, the physicist Paul Dirac wrote down an equation meant to combine quantum mechanics with special relativity for the electron. It worked beautifully, with one deeply uncomfortable side effect. The equation had extra solutions, describing particles with negative energy. Most physicists would have thrown those solutions out as a mathematical glitch. Dirac, to his enormous credit, didn't. He trusted the equation over his own intuition, and by 1931, he'd proposed that these strange extra solutions corresponded to a real particle, an anti-electron, with the same mass as an ordinary electron, but the opposite charge. It's worth pausing on just how unusual that decision was, because it says something about how physics actually makes progress. Dirac was famously a man of very few words, and colleagues who worked with him described someone who trusted mathematical consistency almost the way other people trust their eyes. He's remembered for the view, expressed in different words throughout his life, that if an equation is beautiful, if it's simple, symmetric, and internally consistent, it has a real chance of being true even before anyone finds evidence for it. That's not mysticism. It's a specific, checkable habit. When his equation for the electron produced negative energy solutions that seemed absurd, the easy move would have been to patch the equation to make the embarrassing part disappear. Dirac refused to patch it. He asked what the universe would have to look like for those solutions to be real, and then said so, in print, years before anyone had the tools to check him. That's a very different kind of confidence than being loud or certain in conversation. It's the quieter, riskier confidence of trusting a piece of mathematics over your own gut feeling about what nature should do and being willing to be wrong in public if it wasn't. A year later, in 1932, a physicist named Carl Anderson was studying cosmic rays, high-energy particles raining down from space, using a device called a cloud chamber, essentially a box that makes the faint trails of passing charged particles visible like breath on cold glass. Inside one of those trails, Anderson found a particle that curved exactly the way an electron should curve in a magnetic field, except bent the wrong direction. It had to be a particle with the same mass as an electron and the opposite charge. Dirac's strange, unwanted extra solution had a real physical double, sitting in a photographic plate in a laboratory in Pasadena. Here's what makes this genuinely remarkable, and it's the part most retellings skip past too quickly. The mathematics predicted a brand new kind of particle before anyone had ever seen one. Not after the fact, dressed up to explain a mystery. Before, Dirac followed his own equation into territory that seemed physically absurd, and nature turned out to agree with the equation, not with anyone's intuition about what should be possible. That's one of the cleanest examples in the history of physics of pure mathematics outrunning experimental discovery, and it's also, quietly, the first real evidence that Feynman and Stuckelberg's later U-turn picture wasn't just a clever trick. It was describing something real happening in nature. It's worth knowing that Dirac's own first attempt to make sense of those negative energy solutions wasn't the clean U-turn picture at all. It was stranger, and in hindsight, almost charmingly awkward. Before Feynman and Stuckelberg's reinterpretation, Dirac imagined something called the Dirac Sea, an infinite ocean of negative energy electrons, already filling up every available negative energy state throughout all of space, invisible to us precisely because every slot was already occupied. An anti-electron, in this picture, wasn't a new particle at all, it was a hole. A single missing electron in that infinite sea, behaving as if it carried the opposite charge simply because something ordinary was missing from an otherwise full ocean. It's an ingenious idea, and it technically worked for electrons. But it was also deeply unsatisfying, because it required inventing an infinite, unobservable sea of particles, filling every point in the universe, just to explain one missing piece, and it didn't generalize cleanly to particles that don't obey the same quantum statistics as electrons. Feynman and Stuckelberg's reinterpretation threw the infinite sea away entirely and replaced it with something far simpler. No ocean, no hidden filled states, just a single particle's path, occasionally running the other way through time. Simpler explanations that also work better are rare in physics. This was one of Feynman's reinterpretation went further than just explaining what a positron is. It explained why every single particle in nature must have an antiparticle counterpart, without exception. If any particle's world line, drawn correctly, according to the mathematics, is even in principle allowed to double back through time, then that backward segment will always look, from our forward-moving perspective, like some kind of antiparticle. It isn't a special rule added on for electrons. It's a structural feature of how particles are described at the deepest level physicists currently have access to. Protons have antiprotons. Neutrons have antineutrons. Quarks have antiquarks. One mechanism, applied universally. You can actually watch this rule play out inside a particle accelerator, and it's worth knowing what you're looking at when you see footage of one. When two protons collide at very high energy at a facility like CERN's Large Hadron Collider, some of that collision energy converts directly into new particles, and whenever a new particle of matter is created out of pure energy that way, an antiparticle partner is created right alongside it, in the same instant, every single time, no exceptions ever recorded. That's not a coincidence physicists find charming. It's the same structural requirement Feynman's picture demands. Create a forward-running world line, and you've necessarily created the possibility of a backward-running segment paired with it. Every particle-antiparticle pair ever produced in every collider experiment in history is a live demonstration of that single rule, running continuously in laboratories right now. Here's where this video has to slow down and be careful, because this is exactly the point where a lot of exciting-sounding explainers quietly stop being accurate. The positron is an electron moving backward in time is a genuinely correct, genuinely useful, professionally standard way physicists talk about and calculate with antiparticles. It is not the same claim as electrons can time travel. Nobody has ever sent information, or a macroscopic object, or a signal of any kind backward through time using this mechanism, and nothing about this interpretation lets you do so. What Feynman and Stuckelberg gave physics was a mathematical reinterpretation, an extraordinarily productive one. Since it's the actual engine behind every Feynman diagram, physicists still draw today, not a discovery that time travel is physically achievable. Here's how physicists themselves would defend taking this picture seriously anyway, rather than dismissing it as just math. It makes predictions, and those predictions are checked against reality to an almost unbelievable degree of precision. The magnetic moment of the electron, a number describing exactly how strongly an electron behaves like a tiny magnet, has been measured in the laboratory and separately calculated using this exact sum over all paths, including backward in time ones framework. As of a 2022 measurement, refined at Northwestern and Harvard, the calculated and measured values agree to roughly 1 part in a trillion, not 1 part in 1,000, not 1 part in a million. 1 part in a trillion among the most precisely verified predictions in the entire history of science. That agreement is why physicists keep using this framework, and why it's fair to call it one of the best tested ideas in physics, while still being honest that best tested mathematical framework and literally true account of time itself are two different claims. The math works spectacularly. What it means, at the deepest philosophical level, about the true nature of time, remains a genuinely open question that physics hasn't settled. Holding both of those things at once, this works better than almost anything else humans have ever built. And we're not certain exactly what it's telling us about reality is not a weakness. It's honesty, and it's worth more than a tidier, overconfident story. It helps to know what a Feynman diagram actually is, since this video keeps leaning on the phrase. It isn't a piece of art, and it isn't just a teaching cartoon. It's a precise bookkeeping tool, a small picture of lines and vertices where every line represents a particle traveling somewhere, every junction represents an interaction, and this is the part that matters. Every diagram corresponds to an exact mathematical term that gets added into a calculation. Want to know how two electrons scatter off each other? You don't draw one diagram. You draw every diagram. Physics allows for that process, simple ones where a single photon passes between them, and increasingly baroque ones where extra particles flicker in and out of existence along the way and add up every single contribution. Some of those flickering, temporary participants are exactly the backward in time segments this video has been describing. A piece of a diagram that, read one way, is a particle briefly running the wrong way through time, and read the standard forward time way, looks like a positron popping into existence and vanishing again a fraction of an instant later. Nobody observes these directly. They're called virtual for a reason. But leave them out of the sum, and the final calculated number stops matching experiment. Include them, and it matches to 1 part in a trillion. Here's a little bit more on why that particular measurement carries so much weight. The electron's magnetic moment isn't calculated by writing down one clean equation and solving it. It's calculated by adding up an enormous number of different possible ways an electron could interact with the quantum field around it, each one drawn as a Feynman diagram, and this is the part that matters here. Some of those diagrams include exactly the kind of backward-in-time loop this whole video has been describing. A virtual particle briefly popping into existence, running the wrong way through time, and vanishing again before it could ever be directly observed. Leave those backward-in-time contributions out, and the calculation stops matching reality at high precision. Include them, exactly as Feynman's framework says you should, and you get an answer correct to 1 part in a trillion. That's not a hint. That's about as strong a piece of the math is doing something right evidence as physics has ever produced for any idea anywhere. Now, for the second half of the mechanism, the half almost every competing explanation leaves out entirely. If antiparticles are just as real, just as stable, and just as physically valid as ordinary particles, an obvious question follows. Why isn't the universe an even 50-50 split of matter and antimatter? Why are you, and everything you've ever touched, made overwhelmingly of one side of that split? For decades, the working assumption was that nature treated matter and antimatter as perfectly symmetric partners in every respect, same mass, same behavior, mirror images of each other in every conceivable way. That assumption held up right up until 1956 and 1957, when physicist Chien-Shiung Wu ran an experiment that quietly broke physics. It's worth being precise about how this happened, because it's a genuinely clean example of theory and experiment working exactly the way they're supposed to. The experiment wasn't a lucky accident. In 1956, 2 theoretical physicists, Tsung-Dao Lee and Chen-Ning Yang, published a paper arguing that nobody had actually ever tested whether parity left-right symmetry held up in the weak nuclear force specifically, even though everyone assumed it must, by analogy with every other force in physics. Lee and Yang didn't just raise the question, they went looking for someone who could test it, and they found Wu. Wu ran the experiment. The result came back within months, and Lee and Yang received the Nobel Prize in Physics in 1957, less than a year after their original paper, one of the fastest turnarounds from prediction to Nobel recognition in the prize's history. It's worth naming that Wu herself, despite running the actual experiment that confirmed the effect, did not share in that particular Nobel Prize, a point historians of physics still discuss when talking about how credit gets distributed between theorists and the experimentalists whose work confirms them. Wu's setup used a radioactive isotope called cobalt-60, cooled to nearly absolute zero and placed inside a magnetic field strong enough to line up the spins of its atomic nuclei in one consistent direction. Cobalt-60 decays through a process called beta decay, spitting out electrons as it does. If nature really didn't care about left versus right, if the universe were what physicists call parity symmetric, those electrons should fly off equally in every direction relative to the spin axis. Wu found they didn't. The electrons preferred one direction, decisively, reproducibly. Nature, it turned out, does distinguish left from right. Physicists had assumed for decades that it couldn't. They were wrong, and the Wu experiment proved it in a matter of months. Here's why that result matters far beyond left and right. If nature secretly prefers one-handedness, the natural next question is whether it also secretly prefers matter over antimatter. And the answer turned out to be yes, though the relationship is more subtle than a simple asymmetry. It took combining 2 separate broken symmetries, the parity violation Wu discovered, plus a related asymmetry between matter and antimatter called charge conjugation, to find that the combination of the two, called CP symmetry, is also violated, just slightly. That small violation is the crack in the mirror that let one side of the universe win. There's a genuinely strange side effect of Wu's discovery worth pausing on, because it answers a question that sounds almost too basic to have ever been unsolved. Before her experiment, there was no way, using only the laws of physics themselves, to define which direction is left and which is right. You could point at something, sure, but that only works if you and the other person already share some common reference, some way to compare. Send a description of left over a radio signal to somewhere with absolutely no shared frame of reference, and before 1956, physics genuinely had no built-in universal answer to hand over. Parity violation changed that. Because beta decay always sends its electrons off preferentially in one specific direction relative to nuclear spin, you can now describe an experiment in pure physics terms. Cool this isotope, align its spins this way, watch which direction the decay electrons prefer, and get a consistent physical definition of handedness, valid anywhere in the universe. No shared frame of reference required. It's a strange kind of question to have needed an experiment to answer, and it's exactly the kind of quietly profound consequence that gets lost when a story about antimatter only tells half of it. Here's the number that actually explains why you exist at all, and it's worth sitting with because it's almost absurdly small. In the earliest moments after the Big Bang, matter and antimatter were produced in what should have been almost perfectly equal quantities. As the universe cooled and expanded, virtually all of that matter and antimatter found each other and annihilated, converting back into pure energy, gamma rays flashing across the newborn cosmos. Virtually all of it, but not quite. Because of that tiny CP violation, for roughly every billion matter-antimatter pairs that annihilated each other into nothing, one single extra particle of matter was left standing, with no partner left to annihilate it. Every star, every planet, every atom in your body is built entirely out of that 1 in a billion left over. You are not made of the normal stuff. You are made of the tiny, lopsided residue of an almost perfect act of mutual annihilation that consumed everything else. If that CP violation had been exactly zero, if matter and antimatter really were perfectly, flawlessly symmetric, there would be no galaxies, no stars, no planets, no you. Just an expanding cloud of photons, forever, with nothing left to build anything out of. This is where the U-turn picture and the scarcity story turn out to be two views of the exact same underlying mechanism, not two separate facts bolted together. The same deep symmetry that Feynman's time reversal picture depends on the idea that flipping charge, flipping spatial handedness, and flipping the direction of time together should leave the fundamental laws of physics unchanged. A principle physicists call CPT symmetry is precisely the symmetry whose narrower pieces, parity alone, then CP alone, turned out to be broken. Antimatter exists, without exception, because every particle's world line is allowed to run backward through time. Antimatter is almost entirely gone because the deeper three-part symmetry that would have kept matter and antimatter perfectly balanced isn't quite perfect. It's broken by a hair, in exactly the amount needed to leave one part in a billion of the original matter standing, forming everything you can see. Existence and scarcity aren't two separate stories about antimatter. They're the same symmetry, examined from two different angles. Here's an honest coda to the scarcity story. Because almost all of it annihilated in the first fraction of a second is a strong claim, and strong claims deserve someone actually checking. Since 2011, an instrument called the Alpha Magnetic Spectrometer has been bolted to the outside of the International Space Station, sifting through billions of cosmic ray particles for one very specific thing. Any sign of naturally occurring antimatter heavier than a stray positron, which would hint that some pocket of the universe, somewhere, escaped annihilation and is still made of the other kind of matter. As of the early 2020s, out of billions of ordinary helium nuclei detected, researchers flagged a small handful, fewer than 10, of candidate events that looked like anti-helium nuclei, and they have been extremely careful not to declare victory because contamination and instrument error are entirely plausible explanations for a handful of ambiguous events amid billions of readings. That caution is exactly what good science looks like, a real, sensitive, ongoing search, reporting an intriguing but unconfirmed handful of candidates rather than a headline. If it's ever confirmed, it would be one of the biggest discoveries in the history of physics. Right now, it's an open question, and this video would rather tell you that honestly than dress up a handful of ambiguous events as a settled discovery. It's worth explaining why this search even has to be this hard, since it raises a reasonable question. Couldn't we just look at a distant galaxy and tell whether it's made of matter or antimatter? Unfortunately, no, and the reason is itself a neat piece of physics. An antistar, made entirely of antiprotons and positrons instead of protons and electrons, would burn by the same nuclear fusion process as an ordinary star and give off exactly the same light, the same spectrum, the same everything, because light itself carries no charge and behaves identically either way. You cannot tell matter and antimatter apart just by looking at the light they emit from a safe distance. The only way to know for certain is either to find direct physical contact, a boundary region where matter and antimatter regions would be annihilating each other and producing a very specific, very bright signature of gamma rays, which nobody has ever conclusively observed at the scale a large antimatter region would require, or to catch a stray antimatter particle in a detector, the way AMS-02 is trying to do. That absence of any large-scale annihilation signature anywhere we've looked is itself strong indirect evidence that there's no significant antimatter region nearby in the universe, even though it can't rule out something small and distant. None of this is purely theoretical, either, and this is worth knowing, because it's easy to assume something this exotic-sounding must stay locked inside equations forever. In 2002, a team working on an experiment called Athena at the CERN laboratory in Switzerland successfully created the first cold antihydrogen atoms, antiprotons, paired with positrons, forming actual atoms of antimatter built the same way ordinary hydrogen is built, just with every particle swapped for its antiparticle. In 2010, a follow-up experiment called Alpha went further, actually trapping antihydrogen atoms, holding 38 of them in place using magnetic fields for over 1/10 of a second, long enough to study them directly rather than watching them annihilate on contact with ordinary matter an instant after forming. Trapping is the hard part, and it's worth knowing why. Antihydrogen atoms are electrically neutral overall, so you can't just steer them with charged plates the way you'd steer a bare antiproton. Alpha's solution was to use a carefully shaped magnetic field, exploiting the tiny magnetic moment of the antihydrogen atom itself to build an invisible magnetic bottle just barely deep enough to hold the coldest, slowest antihydrogen atoms in place, while faster ones simply escaped and annihilated against the walls. Getting even 38 atoms to sit still inside that bottle for 1/10 of a second required cooling them to a small fraction of a degree above absolute zero and controlling the trap fields with extraordinary precision, a genuinely difficult engineering achievement built entirely to test an idea that, decades earlier, started as an uncomfortable extra term in one physicist's equation. That's the payoff of following strange mathematics all the way to its logical conclusion. Humans built a machine capable of creating and briefly holding the mirror image of the simplest atom in the universe. And every single day, in hospitals with far less exotic equipment than CERN, doctors put a milder version of this same physics to direct medical use, injecting patients with substances that decay by emitting positrons, then watching where those positrons annihilate against ordinary electrons inside the body to build a picture of what's happening in living tissue. Antimatter isn't waiting in some distant, exotic corner of physics. It's already part of how modern medicine finds cancer. Here's the honest answer to the question this video opened its third act with. If antimatter is real, and physicists can make it, why isn't it fueling anything? Science fiction loves antimatter engines, and the underlying physics reason they're appealing is real when matter and antimatter annihilate. Essentially, all of their mass converts directly into energy, which is a vastly more efficient release of energy than any chemical reaction or even nuclear fission could ever manage. But efficient, once you have it, and practical to make, are two completely different claims. And this is exactly where headlines quietly swap one for the other. Making antimatter isn't like mining a rare metal. Facilities like CERN produce antiprotons by smashing ordinary particles together at close to the speed of light and sifting out the tiny fraction of collisions that happen to produce an antiproton, then slowing and storing it without letting it touch ordinary matter, since contact means instant annihilation. A NASA-funded study estimated the cost at roughly $62 trillion per gram of antihydrogen. Other estimates, accounting for different production methods, run even higher. At the production rates realistically achievable with current technology, it would take on the order of 100 billion years of continuous operation to accumulate a single gram far longer than the current age of the universe. Antimatter isn't rare because nature is stingy with the idea. It's rare because making it, one particle at a time, fighting against the same asymmetry this whole video has been describing, is almost the most difficult and expensive thing humans have ever attempted to manufacture. So when you see a headline or a video implying antimatter propulsion is right around the corner, the honest version of that story is this. The physics of the energy release is real and spectacular, and the physics of actually accumulating usable quantities is, with current technology, close to impossible. Both halves are true at once, and leaving out the second half is exactly the kind of quiet exaggeration this video is trying to train you to notice. Once physicists could actually trap antihydrogen instead of just creating it, an obvious question followed almost immediately. Does gravity treat antimatter the same way it treats ordinary matter, or could antimatter somehow fall upward? Science fiction has toyed with anti-gravity antimatter for decades. In 2023, a follow-up experiment called Alpha G finally tested it directly, releasing trapped antihydrogen atoms and precisely timing which way they drifted under gravity alone. The result? Antihydrogen falls down, just like ordinary matter, at a rate consistent with the same gravitational pull that governs everything else, measured to a precision of roughly 20% so far, with physicists already planning follow-up runs aiming for far tighter precision. It's a quietly satisfying result, exactly because it isn't exotic. The universe's strangest substance obeys one of its most ordinary rules. Here's the reframe worth sitting with. Antimatter sounds, on first hearing, like a name for something fundamentally other, a different substance, from a different rulebook. It isn't. It's the same rulebook, read from a different angle, a world line, described correctly, running backward through time instead of forward. And the reason there's so little of it left isn't some separate cosmic accident bolted onto that story. It's the same deep symmetry, cracked by the tiniest possible amount at the earliest possible moment, leaving behind exactly enough leftover matter to eventually build stars and periodic tables and a species curious enough to go looking for the crack. Notice, too, what this reframe quietly does to the word exotic. Nothing in this video required anything genuinely alien to explain, not a new force, not an extra dimension, not a rule imported from outside known physics. Every piece was already sitting inside equations and experiments physicists had access to for most of the 20th century. What made antimatter feel exotic was never the underlying mechanism. It was that almost nobody had walked through both halves of the mechanism back to back, in one sitting, and let them explain each other. What do you actually do with an idea like this? Here's the honest, non-mystical version. The next time you read a headline claiming some new discovery, breaks the laws of physics, or proves time travel is possible, you now have a genuinely useful filter to run it through. Does this claim describe a mathematical reinterpretation that makes precise, checkable predictions the way Feynman's backward-in-time positron does, tested to 1 part in a trillion, or does it describe an actual, physical violation of cause and effect that nobody can check at all? Those are different categories of claim, and conflating them is exactly how a real, extraordinarily well-tested piece of physics gets flattened into a much less honest headline. There's a practical version of that filter you can actually use this week. When a claim about antimatter, or relativity, or quantum mechanics shows up on your feed sounding dramatic, ask 2 questions before sharing it. First, is there a specific named source, a paper, an experiment, an institution attached to the number being quoted, or is it just scientists say? Second, does the claim describe a checkable prediction with a precision attached to it, the way 1 part in a trillion, or 20% precision, are precisions you could in principle go check yourself, or is it a vague assertion with no way to verify it at all? Real, well-tested physics almost always comes with exactly that kind of specificity attached, because that's what makes it checkable in the first place. Claims that resist being pinned down to a source, a number, or a method are the ones worth treating with the most skepticism, antimatter or otherwise. There's a second, quieter implication too, and it's less about physics headlines and more about how you think about your own existence. Everything you are is downstream of an imbalance so small that for every billion pairs of particles that canceled each other out perfectly, only one survived to become you. That's not a comforting, tidy kind of existence, no grand design, no inevitability, just an asymmetry so small it's almost a rounding error, magnified by billions of years into everything you can see, touch, and be. Some people find that unsettling. It's worth trying, at least once, to find it the opposite. Astonishing that a leftover this small was enough. There's a third implication too, smaller but worth carrying with you. Notice how many separate pieces had to line up honestly for this one story to hold together. A theorist trusting an ugly-looking equation over his own intuition. 2 other theorists asking a question nobody had bothered to test. An experimentalist willing to run a hard, cold, months-long measurement to answer it. Decades later, an instrument bolted to a space station, patiently sorting through billions of ordinary particles for the rare exception, openly admitting it hasn't found a confirmed answer yet. None of these people needed to exaggerate anything. The real story was already strange enough. That's a pattern worth watching for well outside of physics. The accounts that hold up under scrutiny are usually the ones that were never dressed up to sound more dramatic than the evidence actually supported. Every atom in your body survived an annihilation event so close to total that it consumed essentially everything else that ever existed alongside it. You are the leftover, not the plan, not the point. The remainder, from a subtraction that almost came out to zero, there's something worth sitting with in that, the same way there was something worth sitting with in the fact that a hospital, somewhere near you, is quietly using genuine antimatter annihilation to look for a tumor at this very moment. The most exotic idea in this entire video, matter running backward through time, isn't sealed away in a physics department. It's sitting in a diagnostic imaging suite, doing ordinary, useful, unglamorous work, the same physics, wearing a lab coat instead of appearing in a headline about time machines. Feynman spent a career insisting that the goal of physics was never to make nature sound more mysterious than it is. It was to find the plain, checkable mechanism underneath the mystery, and then have the honesty to say clearly which parts of the story are settled and which parts are still open. This video has tried to hold to that same standard, a real mechanism tested to 1 part in a trillion where it can be tested, openly uncertain where it still is, applied to a question, why does anything exist at all, instead of nothing that is about as large a question as physics ever gets to ask. If a positron really is just an electron running the other way through time, what do you think now actually means to a particle that, in some real mathematical sense, doesn't experience time the direction you do? Tell me, did the existence half of this story surprise you more, or the scarcity half? Most people have only ever heard one of the two. If you want physics that connects the pieces, other explainers leave scattered existence and scarcity, math and honest caveats, laboratories and hospitals, that's what the Physics Storyteller exists to do. Subscribe to the Physics Storyteller. Next time on the Physics Storyteller, we go looking for another piece of physics that sounds like 2 separate mysteries and turns out to be one. You are not separate from the story in this video. You are its answer. 1 part in a billion, standing here, asking why.